So thank you for joining me today for this workshop. So this is actually two workshops stacked on top of each other. So it's going to be building with Neurotech, and then it's going to be more of like a neuroscience specific workshop. But they kind of build off of each other, and I'll pause for sort of questions at the end of this one, but then I'll go kind of directly into the other one. So if you want to stay, you can. If you have somewhere to be. But then I'll just kind of lead into the next one. So I just mentioned that because it's kind of billed as one and then the other. So my name is Ruby Princeton. So I'm a PhD student here at the University of Alberta in psychology, and I'm supervised by Dr. Cor Beervelt. And I have a BA in psychology from the U of A as well, and a master's in mind, language, and embodied cognition from the University of Edinburgh. And I'm also the educational lead at NeurAlbertaTech. So my area is in embodied cognition and technically in philosophy of mind. So it argues that the models of the mind don't include enough contextual information about the body, environment, and other people. And so you'll see that a little bit in sort of the little anecdotes I have in these slides as well, but I'll kind of pepper it in. So if you have questions also about that, I'm very happy to answer questions about my own area. But part of why I bring this up is not only because it's what I'm in, but also kind of I'm about to launch into a little bit about biosignals, which will also include that as well. So I'm going to talk about neurotech and the applications of neurotech, and then threaded through it, I'm going to talk a bit about the challenges as well. And so the hope is from this sort of presentation that you can dissect or approach the problem and consider what the tech has to offer and how to address sort of the questions and limitations from the tech as you have it. And so neurotech is a method or device which interfaces with the nervous system to monitor and modulate neural activity. So it's a biosignal. And a biosignal is received by the body and translated by the brain. So it is also something that can be continuously measured as the body is always intaking and translating things from the environment. I accidentally left like a little thing there. So to broadly envision the breadth of biosignals that we can measure from the body, we're going to start with looking at the 5 senses. So each sense translates environmental information using receptors. This information is transformed from the environment into a signal, which is relayed for further processing. So each signal relies on different receptors, and they all translate to electrical impulses, which we can then measure using a variety of sensors. So you can think about chemical, optical, and mechanical here. And as for neurotechnology, you can also kind of divide that up into two different sections, into neuroimaging and neuromodulation. So I'll give examples kind of both as we go through it as well. But we think of like neuroimaging is used as a way to understand the brain and neuromodulation as a way to alter the brain. And so there's a couple of key principal components of neurotech for this. So when we slice up neurotech, we can do this by looking at how we're measuring it, as in the signal, and where, so the region of interest. And each piece of tech has a few considerations as well. So like I said, it's domain of information and the regions of interest. But then there's also considerations for how you're going to apply that neurotech. So you have cost, mobility, accessibility, sector, and business model. So this chart represents modalities based on what domain of information they're tapping into. So again, this is similar to what I was bringing up before with electrical, optical, and magnetic, but you have sort of they're segregated into those different sections there. And the first of which is ePhys. ePhys is the most common neurotech and also generally the cheapest. And I think Nat has like the most equipment kind of in this area as well. So there's more that can be like sort of used with it. So it measures electrical potentials with electrodes, which is direct measure of neuron activity. And so it detects those bioelectrical potentials, which I'll explain later. But you can now think of it as like electrical activity of the tissue of interest recorded by electrodes, which is the individual sensors. And you can see that here with all the electrodes for what would be like basically a research level EEG. And so we can measure tissues of interest composed of neurons. So that would be the EEG, or of muscles. So we're looking at contractions of muscles, muscle fibers, spindles, as initiated by nerve cells. So you can see, so you have EEG, and then you also have different areas of the body essentially that also are involved in that electrophysiology. And so you have muscles, and you have heart, and you have the eyes as well. And these are direct measures of neuronal activity. But then we also have two more invasive measures as well that would be part of the same category, which actually involve measuring the brain itself. So ECOG places electrodes on the actual surface of the brain, the actual like surgical surface of the brain, and deep brain stimulation, which inserts electrodes into the brain tissue. And so I imagine you probably wouldn't be likely to use those anytime soon. And then you can also look at optical imaging. So it's concerned with measuring the reflectance or absorbance of light through different tissues using optoids, which is individual sensors. Optodes, sorry. So this is based off of like the basic principles of light and how it interacts with different tissues, and then looking at the ratio of absorption of different wavelengths. Then you can use kind of create inferences about the state of underlying tissue. So you could have a source or an emitter and then a detector at a different point, knowing the properties of the underlying tissue. So you can make deductions about the functioning of the underlying tissue. You can then add additional emitters or detectors to increase your accuracy, varying the distance between the change in the depth of target tissue of interest. So this often includes different wavelengths of light in the same device, and they're typically considered indirect measures of neuronal activity. And so there's two examples here. One is FNIRS, which I believe Nat has a pair of eyeglasses that use this. So this looks at the ratio of oxygenated versus deoxygenated hemoglobin changes in tissue. And then we also have the PPG, Nat doesn't have the PPG. I have the PPG here, which looks at heart rate, blood pressure, and respiration. And so I know that mainly it can measure also blood volume, which means that I'm actually more knowledgeable, or I've read more papers that have looked at that for looking at things like sexual arousal too. You can measure that using that. And then we have MPhys, which is magnetophysiology. So that measures perturbances in magnetic fields, an indirect measure of neuronal activity. And so we can get so we have a couple of different kinds, and they're you have the MRI, which is pretty common. Usually people will compare EEG to MRI. An MRI looks at blood oxygenation concentration, and then the TMS, which includes electrical signals with the magnetic coils, which I'm actually going to use as an example at a later point, because that involves modulation as well. So this one is usually used for looking at locations of things, looking at imaging, and then this one usually includes modulation of actually stimulating and changing brain activity. And so we can basically carve this up in a couple of different ways. So like I said, there's electrical, optical, and magnetic, and that would be based off of the domain of information. So how we're collecting this information, the signals essentially that we're measuring to look at it. But we can also look at it based off of regions of concern, which would be the brain, the body, or the organ-based measures. So basically where you're measuring, what you're concerned with in that measurement. And so that's just another way of categorizing. So you might be asking what the most likely bioimaging modality would be appropriate for dissecting what you want to study. And so if we're interested in a particular disease or disorder, it's worth considering what the most effective device would be for that. And so we know that certain modalities are indirect measures of brain activities and others are direct. And this can also affect time scale, and the spacing of sensors are also related to the spatial scale. So you have temporal on the bottom and spatial, or you have temporal on the x-axis, if I go back to my grad school training here, and on the y-axis, you have the spatial resolution. And so they all have pros and cons, and the best one depends on the disease that you're measuring in question, or the sort of study that you want to do, and the constraints you might have. And so you can see that something like electrophysiological imaging is high on temporal and low on spatial. So it's something that's better for a time series data, or looking at something that might occur in time, or specific events that you want to look at. It's usually a little bit more mobile too. But the electrodes on the scalp don't give us exact locations. You can't you can kind of locate the lobes of where things are happening, but you're not going to be able to directly determine the location. You can do this a bit more with ones that are more invasive, so single cell electrodes inside of the skull, but it's not typically done on humans. Again, a little bit with treatment, but not so much with actual research. And then there's metabolic, which is low temporal, high spatial, usually measuring blood, but you can't move, and the actual measurement is much more static. So again, with something like fMRI, where you might get high resolution, a really clear picture of where something is in the brain, but you can't move. You're going to be stuck in the machine, right? So you're not going to be able to measure someone who's moving in a space, or doing a big activity. Sort of, it's going to be constrained by how you can kind of hold yourself. And so cost is another consideration for this as well. So this is often based on what you're measuring, essentially. So magnetic is usually more expensive, and optical, and then electrical. And this kind of follows some logic in that you can't build your own chamber for an MRI. So it follows that line. And it also has to do with the history. So an EEG is one of the oldest. It's over 100 years old, and so it's a little bit cheaper to make. And but you can also see that there's some exceptions as well. So something like the PPG is going to be slightly cheaper, and then anything that's like really invasive is going to be more expensive. Just you kind of would hope that it would probably be more expensive. Otherwise, more people would probably do it. But it also reminds me a bit of an assignment I once did where we were told that we had to kind of create our own research task based off of like consciousness and perceptual awareness. So like what you can see, or like what state of sort of consciousness you're in. And part of the rubric was actually determining what equipment you could use, because almost everybody defaulted to using an MRI. They were like, this is the golden ticket, this is what you should always use. And the instructor was like, that's great, but it costs like $600 an hour to have an MRI. It includes having a technician there to help you. It includes booking things in a hospital. So it's very difficult to actually do. And so there's a couple of other factors that also go into the accessibility and expense of Neurotech, which includes what it's used for. So research, I think, is an interesting case because I'm in research. But often the equipment itself isn't very expensive if like a PI wants to use something. And so the concept of it isn't, but very few people use it. So it can be quite specialized. And so sometimes you'll need technicians or people to create the equipment for you. And so that's one reason that it might not be super cheap. And then again, like I said, so there's like external versus invasive. So the more invasive it is, the more expensive it's going to be, and also the more likely it's going to be clinical as well. And then if it's open source, of course, it's going to be the cheapest. And so there's 3 different like branches that you can kind of look at for the application of Neurotech. And so I'm going to look at sort of the neuroimaging and neuromodulation use case for each of the 3 applications here. So the first one is medical. And so Neurotech uses diagnostic tools like advanced neuroimaging and brain monitoring devices that aid in the early detection of neurological disorders and informing treatment plans, including guiding surgical interventions. And neurostimulation methods used to manage pain, improve recovery after injuries, and improve prognosis from neurodegenerative disorders. Okay. And so the first one is probably the one that you're most familiar with if you're going to think about neuroimaging. This is an MRI. So in image A, you can see a scan that's used to detect a tumor. So this one here. And image B is a scan during surgery to detect changes in the brain, so that it helps surgeons readjust or reroute their plan as they go. And then you also have this one as well, and that has a similar approach, which helps localize and remove a tumor, but it has both fMRI, so functional MRI, and it also uses diffusion tensor imaging. So fMRI was used to map the cortical structures, which measures brain activity through the blood oxygen dependent changes in the brain during tasks. And DTI was used to map subcortical structures. And that measures brain activity through diffusion of water in the brain. So cortical is, I think of subcortical as almost like the lizard brain in the brain and then kind of around it. So it's like, oh, they were kind of measuring 2 layers of the brain, so to speak. So this was just to make sure that everything was okay with brain activity and brain regions after. And real-time fMRI can also be used during operation to track changes almost instantly in comparison to traditional fMRI. So this allows us to localize the brain areas and where the imaging is non-invasive, but it can also be very expensive. And this is an example of neuromodulation, which is the use of deep brain stimulation to treat patients with Parkinson's. So the electrodes are implanted into key areas, which in this case is the subthalamus, oh my God, nope, never mind. I give up. It doesn't matter, to be honest with you. It's subcortical. It's going deep into the brain again, which involves movement control. So these electrodes are connected to neurostimulators that are under the skin around the collarbone. So right here. And they send a controlled electrical signal to the target brain regions, altering brain activity to alleviate symptoms like tremors. But it can also do things like alleviate seizures in epilepsy as well. But it also requires neuroimaging because the implantation of neuromodulators are guided by neuroimaging. So you can see in the top right image that there's a placement of the electrode here. And that the bottom right, which is the placement during a CT scan, which is yet another neuroimaging technique, which can help with the accuracy of that here as well. So it can improve or alleviate symptoms for neurological disorders, but it's expensive, invasive, and requires maintenance. So it's an example where it's like, where you'd only use it if it truly improved someone's quality of life to be able to use something invasive like that. So as for research, in academia, neurotechnology supports research into neural behavior, helping to unravel complex brain mechanisms and their relationship to behavior and cognition. It also enhances data analysis techniques in neuroscience, allowing for more in-depth studies and discoveries. So this is me. And this is more of my area. So this is a very sexy photo that I took as a selfie while I was in one of the cages for EEG. So I'm wearing the EEG cap. This is like a research level cap. It's 256 electrodes, and it's conducted with water. Like you have to dunk it and rinse it and stuff like that. So you usually have water dripping on your face when you're doing these studies, and you're usually wiping away water as you're doing the study, which I'm sure processing is its own thing for making sure that the data is clean enough once you're trying to do that. So we ran a task in a Faraday cage room. So this is basically a room that's in one of the labs at the U of A. And it blocks ambient signals from the environment. So it reduces the amount of noise that an EEG is getting from basically environment so that you can isolate it to the brain as much as possible. In this particular one, it's shared by a couple of different labs. And so I was using this desk here, but you can see there's another desk there for another lab. There's the amplifiers here, which you actually plug into the cap. So you're sitting down at this desk, and then you're plugged in matrix style into this computer, and the technician on the other side uses it. And you can also see that there's also motion trackers, just out of interest. This was just for a different study altogether, but they kept them. So I studied pairs of people looking basically at joint action and attention. So I had a participant who would sit at the desk with the EEG cap. They were the main participant. And then they actually had someone sitting next to them who was responding to the same stimuli that they were, but they weren't like the main participant. They were used to kind of help understand how we sort of change our behaviors when we have someone else who's also in the room with us. And so in this particular task, we measured how fast they responded to targets when they were on either side of a face, just to see how fast someone would respond to a target if the face on the screen looked at the target or didn't look at the target. And the person next to them was also responding to this task as well. And so you were looking at things like, you know, how fast they were responding, but also how fast they were responding to like the space next to the other person versus responding to something else. The stimuli itself doesn't matter as much for the point of this slide, but it was basically a way of looking at sort of like someone's visual attention and then also looking at sort of the impact of space next to someone else and how that might change things. And then another example is neuromodulation. This was actually another study that I did. I didn't do the neuromodulation side, but I did do the behavioral side of this task as well. And so this particular task studied agency and sense of control. And so a person presses a button and hears some sort of tone after. So they have like a response key, they press a button, and then they hear something. And they have to estimate how long it took between when they pressed a button and when they heard a tone, and they have to basically say like where the clock was, like where the hand where the hand was on the clock at a particular moment in time. And so it was measuring that time difference. In the original task, the experimenters used TMS to interrupt movement. And so you can see the coil. The TMS coil was placed on the side of the head where the motor cortex is, which excited nerve cells and sended signals down to the muscle cells and created muscle contractions. So essentially they had involuntary movement when they used the coil. So they had twitches essentially that would happen that would press the button. And so it became an involuntary response where they would press the button based off of something else moving, and then that would result in hearing some sort of response from them pressing the button. And they also had versions as well. It was a sham condition where they heard the coil, but they got to press the button whenever they wanted. So it was sort of a placebo of whether they thought that the coil was moving their hand or their finger for them. And they found that when participants thought that they didn't have control over their own movements, so either when the TMS did interfere with their movement or when they thought that the TMS interfered with their movement, the estimated time was longer than when they pressed the button. And basically they argued, and it has since been argued, that there's sort of a binding effect that happens where your action and the consequence of your action bind together in sort of one event together. And if you don't think that that happens, you kind of perceive it as being slightly longer. But it was just one way where they were able to manipulate sort of that feeling of control using the TMS coil. And so last is adaptive technology. So these are tools that assist individuals with sensory and cognitive challenges in their daily activities. And it also helps create systems that enhance interaction with technology and improves accessibility and independence. So this is one example, which includes controlling a hex bug using OpenBCI. And OpenBCI is another piece of equipment that NAT lends out. So in this one, electrical signals from the brain are streamed through a device, so hardware and software, to control a hex bug. So let's see if I can. Yeah. And I think there's been like a few projects that NAT has also done with this as well. So like making art with BCI, and I think there was also like a drone at one point too. So those are a couple of examples as well. Let's see if I can. Oh, there we go. Okay, and Recovery X is sort of the last example, and this one uses both neuroimaging and neuromodulation for rehabilitation. So it was developed by GTech as a closed loop BCI system that integrated the two together of imaging and modulation. And so it trains, it helps you train for upper and lower limbs for those who've suffered from motor impairments. So in the case of a stroke, for example, so it connects visual and tactile stimulation, and it can help individuals train for these movements. So they have both a virtual avatar that provides the visual feedback here, but then they also are stimulated by the tactile feedback through the electrical muscle stimulation, which you can see sort of with the pads here and then here as well. And so it helps people connect both the visual and tactile stimulus together. And that helps in activating both sensory and motor function by allowing you to basically relearn how to kind of use those muscles. And so, yeah, so I went through, in sum, I went through categorizing the neurotech modulation modalities in both domain of information and region of concern, and then went through a bit of the cost and accessibility of these technologies and a few examples kind of each one. So that is that for the first workshop. Is there any questions that I've went through for this one? It's a lot of information, so if you don't, that's okay. Okay, thank you. Well, I'm gonna go on the second one, but okay. All right, I think I need to, yeah, exit out of this.